There's limited, yeah, the room we're using is not big enough to hold everyone.
Not using the big dining hall.
They're not, no,
Oh.
and I'm not sure why, but yeah, they're using the old library.
Oh, library, very nice, yes. It's very better, it's nicer, yes.
Yes, so that should be good.
More
Okay.
people are running the college.
So we go. Go ahead. So next we have Peter Ozsvath to tell us how to compute not Floer homology. Not Floer homology, but not with a K.
With a K.
Yeah.
Well, first of all, thank you very much for the invitation to the organizers. It's an honor to be speaking here on Simon's 60th birthday. I'm one of a generation of mathematicians who were drawn to Donaldson's amazing theory of smooth four-manifold invariance. You can tell who we are. You look around and we're all, I guess, we all still think that Paul Zeidel and Richard Thomas are kids, and that and that 60 is the new 30. But anyways, so I'm going to talk about computing not Floer homology. This is a continuation of Zoltan's talk. The two talks even might connect at some point. But I wanted to step back for a moment and draw a little, give a little bit of motivation for what I'm going to discuss. And to do that, so computing not Floer homology. And as Zoltan explained, a knot in a three-manifold is specified by a Heegard diagram, which is a surface of genus G equipped with G red circles and G blue circles. I'm drawing a stupid diagram for some reason. There will be more exciting ones a little bit later. G blue circles, the blue circles are, in this case, the blue circles look like they're related to the red circles, but in general, the blue circles might be quite complicated related to the red circles, but the G-tuple of red circles and the G-tuple of blue circles are all standard individually. So the red circles we'll call alpha circles, and the blue circles we'll call beta circles. So let me not write down too many definitions on the blackboard. The hypotheses are that the beta i's are pairwise disjoint and homologically linearly independent, and so are the alphas. And so this data specifies a three-manifold, and if in addition you choose two base points W and Z, that specifies a knot in that three-manifold. In this talk, my ambient three-manifold will always be S3, and the knot might be interesting. It isn't in this case. Okay, so let me just say very quickly, to this extremely complicated low-dimensional situation, we're going to associate a much higher dimensional symplectic situation, which is we will look at the G-fold symmetric product of sigma, which is a smooth manifold. If you pick a complex structure on sigma, then sim G of sigma, which is the set of unordered G-tuples of points on sigma, is a manifold. It's a smooth manifold. This follows from the little local observation that the symmetric product of C is a smooth manifold, which in turn is this, which is called the fundamental theorem of algebra. A monic polynomial is determined either by its roots or by its coefficients. So this is a smooth manifold, and sitting inside of it, we have a Lagrangian, which is those G-tuples of points where one point lives on each alpha circle. So it's somehow alpha 1 times up to alpha G, called T alpha. That's sitting inside of sim G sigma. And we have also beta 1 up to beta G, sitting on sim G sigma. This is the beta torus. And roughly speaking, what we do is we take the Lagrangian Floer homology of this two Lagrangians inside of the G-fold symmetric product of sigma with the two base points removed. This is loosely speaking, what we do. And this is the invariant that we called HFK hat. Zoltan wrote it as Hij, it's bigraded theory. Let me suppress the gradings for as long as my audience can bear it. Okay, so this is the basic invariant that we would like to compute. Its origins come from understanding Hegardt-Floer homology for closed three manifolds, which has its origins in trying to understand Seiberg-Witten theory for three manifolds, which has its origins in understanding Seiberg-Witten for four manifolds, which has its origins in understanding Donaldson's invariance. So, here we are. So we'd like to compute this. What's that?
Other origins as well.
Probably.
Of course, you have many answers.
That's right. That's right. But that's where, that's where we stop today. Okay. This is what we would like to understand. The generators, I might have said this in a sort of complicated way, but the generators are really just g-tuples of points, which, if you want to write it very, very explicitly, if you number the alpha circles, number the beta circles, T alpha intersect T beta is just the union over the symmetric group on G letters of the Cartesian product of alpha I intersect beta of sigma I. So this is a very combinatorial object. The problem is to compute holomorphic curves that so it's a chain complex, its generators are combinatorial, its differentials are computing some analytic object. Pardon?
I seem to remember in Zoltan's talk there was an arc from Z to W as well.
So if you want to construct the knot itself, then what you do is you draw an arc from Z to W and then another arc from Z to W. One of them doesn't cross the betas and the other one doesn't cross the alphas. And you push the one that doesn't cross the betas into one side, one that doesn't cross the alphas and the other side, and that gives you the knot. So the arc is what specifies the knot.
Are the alphas and betas oriented circles?
No, they're not oriented.
Sure.
Well, depends on how much structure you want.
We don't have that oriented, there's some sign ambiguity, isn't there?
That's right. If you don't orient them, there's a sign ambiguity. I'm working over Z mod 2, but yes.
Oh.
Sorry.
That's cheating.
Okay. So then orient them and there's no sign ambiguity.
Yeah.
Okay. All right. Okay, fair enough. Any other questions? Okay. So this is the invariant we'd like to compute. And so of course, this is, as Zoltan mentioned, this is an invariant that whose definition goes back to 2003. Zoltan and I defined this, and it was also independently discovered by Jake Rasmussen. Okay, and it had applications that Zoltan talked about. So now let's just take this as a point that we'd like to compute. Now, there's a let me just step back for a moment. Remind you that the Euler characteristic of this insuitable sense is related to the Alexander polynomial. And let me describe the computation of the Alexander polynomial by Kaufman states. So this is, you can read about this in Kaufman's book on knots and formal knot theory. So the idea is, so one would like to compute the Alexander polynomial, the knot, give an explicit, here, that's left-handed, let me do right-handed. So we would like to write down the Alexander polynomial knot from looking at a projection. And the basic point is the following. So we take our projection and we mark one of the edges with a star. And we'd like to look at what are called Kaufman states. So what's a Kaufman state? A Kaufman state is a way of arranging dots in one of the four corners adjacent to each crossing, satisfying the following two rules. One is that a dot is not allowed to be adjacent to a star in a region that's adjacent to a star. So my dot's not allowed to live here or here. So he can live here, in this case here or here. The next rule is that no region can contain two dots. So once I've already, this is starred, this is already dotted, so my dot has to be here or here. Let me put it over here just for argument's sake. Then this last guy's constrained to be up here. And that's what a Kaufman state is. I didn't write down the definition in complete sentences. I refer you to Kaufman's book.
So there's a dot at every crossing?
There's a dot around every crossing.
One dot?
One dot, exactly one dot around every crossing. Okay, so let me say this in even more basic terms. So a knot has what's called a checkerboard coloring, where you color the regions in the knot projection. This is, by the way, impossible to do to blackboard. There's a checkerboard coloring where each region is colored black or white, with the rule that each edge separates a black region from a white region. And there's something called the black graph, where you put a dot in each black region and you draw an edge for at each crossing that connects each region. Okay? I know. So that's the right. It's impossible to give this to the blackboard because I don't know what black is. Is it green or is it white? It's not clear. Okay. So so we have
environmentally friendly black.
Environmentally friendly black. Okay. But I can't call an uncolored thing black. Somehow that goes counter. Okay. Sorry. We'll save this discussion for later. But so we have a graph associated with a knot projection, and in this graph we can look at maximal subtrees of that graph. And it turns out that the things I just defined Kaufman states are in one-to-one correspondence with maximal subtrees of the black graph. That's a nice combinatorial object, which might raise the question of then why did I talk about Kaufman states ever? Why didn't I just talk about maximal subtrees of the black graph? And the answer is the following. So I'm going to write down two functions, one of which I'm going to call the Maslov function, which is defined for every Kaufman state. I put -1/2 here, 1/2 here, 0 here, 0 here, 1/2 here, -1/2 here, 0 here, depending on how the knot is oriented. Yes? You see, I didn't define them, but I didn't write them on the blackboard. The Kaufman states were these arrangements of dots around each crossing. I should say what the one-to-one correspondence is. You look at the dot, and if the dot is in a black region, then you include the edge, and if it's not, then you delete the edge. So this Kaufman state right here corresponds to this edge, this maximal subtree. That's just a single edge.
It's the same thing as a spanning.
Yeah. What's that?
You just deleted the ones which have white dots, right?
Yeah, I deleted the ones that have white dots. And, yeah.
Black and white.
Sorry. Okay, great. All right, so now I have an Alexander function, which you get by looking at you orient your knot, you look at where your Kaufman state lives. It lives here, that crossing contributes 0, here the crossing contributes -1/2, etc. You add them up over each crossing, and that gives you a function which goes from Kaufman states to the integers. And there's another function which is the so-called Maslov function, where the local contributions are these. And the theorem, which is Kaufman's theorem, is that the Alexander polynomial of the knot can be expressed as a sum over all Kaufman states of -1 to the Maslov of that Kaufman state times t to the Alexander of that Kaufman state. So it's not exactly how he formulated it, but it's not hard to see that it's equivalent to what he formulated. Okay, so so this is in Kaufman's book. What I should now explain is that back in the day, we found a handy Hagar diagram, one that Zoltan drew on the blackboard, which was naturally associated to a knot projection. Yes?
These functions depend on where you put the dot in the
The star, yes. It depends on where I put the star.
And the dot?
The dot, yeah, of course. It's a function of where the dot lives. Yeah,
Ah, okay. Oh, okay.
yeah. So this is the Hagar diagram that I'll attempt to not erase. We have a alpha circle for each region in the knot diagram. We have a little beta circle near each crossing. These little beta circles, they look like Pringles potato chips. You have those in England? Very crisps. Sorry, crisps. And I have one down here. So one beta circle that's transverse that corresponds to the starred edge, and the elementary observation is that T alpha intersect T beta is simply in the points in here are in a one-to-one correspondence with Kaufman states. And you can see that sort of in the neighborhood of each beta circle you have at most 4 different positions. Let me just draw that kind of blown.
Once you distinguish one of the blue circle.
That's a different. Oh, you can't see it because it's too far down. There's one beta circle that's different from all the others. Sort of locally, it looks like you have sort of 4 different regions where each dot can live. No 2 dots can live in the same region because that would be 2 beta circles intersecting the same alpha circle, and that's the one-to-one correspondence. Okay, so we used this in around 2003 to do some computations, but so you could see what the generators are. We could compute their bigradings in that. So M and A are secretly the bigradings of this chain complex. But computing the generators and their bigradings is not enough to compute a chain complex because there's that nasty differential. So the challenge remained to compute Hagar-Floer homology by putting a differential on Kaufman states. So I'll state a quasi-theorem. This is what we're discussing today. This is in progress. And the statement is going to be vague. So somehow the fact that there exists such a chain complex we knew back in 2003, but there is an explicit algebraic description of a bigraded chain complex whose generators are Kaufman states and whose differentials can be understood explicitly algebraically. And when I say explicitly algebraically, I mean that Zoltan wrote a computer program for actually computing this. You give the program a big knot, and it spits out the answer. And that's the sense in which it's explicit. At the end of my talk, you're going to realize that I haven't actually given you the explicit description, but I will give you ingredients that go into this explicit description. Yes?
This version of the theorem is not in progress. We have written 2 papers on this theorem.
Whose homology? Is HFK hat. Thank you for as someone in the audience pointed out, there are 2 papers where we describe such an explicit complex whose homology is a not invariant, but in progress is this identification with holomorphic geometry, which I would like to discuss. Okay. Are there any questions? So yeah.
tell you anything about the complexity of computing HFK?
I'm sure it does. The point is that sorry. Let me put your question on hold. I should just point out that in 2006 there was a Manolescu, me, and Straight Sharkar gave another combinatorial description of not Floer homology, where the holomorphic disks we were computing were just rectangles embedded in a torus. So they were fantastically simple. However, for an n crossing naught, there are roughly n factorial generators. So in practice, that is not computable, you're computing the homology of a chain complex that's simply far too big. So I'm going to beg your question by saying that here's a chain complex whose generators are like spanning trees, and you know that that's sharp in some sense. For an alternating knot, the differential vanishes. So you expect, in the worst case, to have a chain complex this big. Okay. Any other questions? Okay. So let me tell you. What should I say next? Okay. So the basic project here, as Zoltan explained, was that what we would like to do is we'd like to take this Heegard surface and we would like to degenerate it. And we're going to have a very specific type of degeneration. We're going to cut the Heegard surface into two pieces. And we're going to cut the Heegard surface into two pieces in such a manner that at each of the cuts you have, somehow we have 2n circles, where n is some number, some even number of circles. And we cut our alpha circles so they cross these cut points. Yes?
N is the center of every cut.
Say again?
N is the center of every cut.
No, n can vary at each different cuts. But right now there's only one cut. Okay. So we cut also our alpha circles so that now they're just alpha arcs. And the alpha arcs are going to look like a linear graph. So you might say, why do they have to be a linear graph? Probably there's a theory where you don't have to have them be a linear graph. Algebra would be more complicated. So I want to just look at that case. So we're going to cut our surface in such a way that the cut consists of 2n circles. None of those circles cross any beta circles. They cross only exactly alpha circles. And the pattern is that you have these alpha arcs, 2n minus 1 alpha arcs that connect them. Okay, so this is the manner in which we're going to cut our surface. And morally speaking, what we would like to do is we would like to look at, we're going to take the g-fold symmetric product, and what we would really like to do is we would like to sort of develop nodes at sigma. We want to, as our gauge theory roots suggest, we would like to put in long cylinders transverse to this cut, let the limit go to infinity, see what kind of holomorphic curves we get. So that's the idea, and that turns out not to be enough. So we're going to that's the first step of a theorem that allows one to reconstruct the holomorphic curves in this picture in terms of the holomorphic curves in pieces. But it's only one step. So I'll explain the other steps in due course. But as Zoltan mentioned again, we're really going to slice it up into lots of different pieces. And what we want is for each piece exactly one thing to happen, one interesting thing to happen. We compute some holomorphic curves in some very standard piece, and we stick them together to reconstruct the holomorphic curves.
I'm getting a bit sleepy this time in the afternoon, but to write this down in intelligible fashion must be a horrendous task.
Yeah, I'm going to try it.
No, you don't want to write down. If you want to write this into a paper.
Yeah, I'm trying that too.
I can imagine a movie you might do it. I'm sure you can do it on paper.
Okay, well, so I'd like to explain some of the ingredients that go into this description. So in fact, I would like to discuss a part of this project where instead of cutting it into a bunch of pieces, I'm just going to cut it into two pieces. And I'd like to sort of explain what kind of holomorphic object we associate to the top, what kind of holomorphic object we associate to the bottom, and how we glue them together to get a holomorphic, the total holomorphic object. And then I'm going to explain why that description gives you the right thing. And when I'm done with that, there will be world peace. Okay, but so let me start with just an expression of algebra. And before I started, yes.
I'm a little confused about this comment about the kind of linear tree. Are you explicitly identifying the plane with one of the halves of the surface, or is this a kind of formal thing?
I mean, to say it very explicitly, what I'd like to do is I'd like to pick this, 2n plus 1 punctured sphere. Think of this as an actual surface. Stick that into your Hegardt surface by a homeomorphism. And
So like you're assuming there's no genus.
yeah, so there's genus and stuff, but genus is happening. Here's genus. I mean, somehow like these guys might go through genus as far as we're concerned, but sort of this is the picture. Any other questions? Okay, so I'm at the following advantageous situation that Misha Gromov apologized that he would have to leave halfway through my talk, and Sir Michael said that he's sleepy. So now I'm going to be able to.
Good time. I have halfway through the talk.
So I'm going to now try to describe some algebra. And I'm not going to define an algebra. I'm going to define an algebraic structure which is completely well known to the symplectic geometers. So I apologize. But so the algebraic structure that I'd like to describe is a we're going to work with a curved algebra. So really, I should say this is a DG algebra. What's a DG algebra? A DG algebra is a vector space with an endomorphism that I'm going to denote by dot, and a preferred element, which I'm going to preferred. So this is a bivalent vertex, and this is a univalent vertex. This is the curvature, and it's supposed to satisfy some structure relations. So the first structure relation is that that the differential of the curvature is 0. And the second one is that if I try to square the differential, then I get the commutator. Right, so I'm sorry, this is horrific, but I'm working mod 2, so I apologize. There should be signs.
So the first thing's D, and the second thing's F.
This is D, and this is, if you like, F. Curved, yeah. Yeah, so the derivative of F is 0. D squared is commutator with F. And it's supposed to be actually, let's simplify life. We're going to have no differential graded. It's going to be just an algebra. So I'm going to, yeah, it's going to be just.
It's already in the notes.
What? Sorry, these are notes that are like evolving over time.
The fork is the multiplication.
Yeah, and the fork is the multiplication. Thank you. So so if I delete the dot, then there's no hypothesis here, and this hypothesis is simply that my curvature is central, and as
Can I ask a question?
Yes.
Waking from my sleep.
Yeah.
Is a curved algebra the same thing as an algebraic curve?
No.
Oh.
Sorry.
Duality, obviously.
That's possible. That's beyond me. That's above my pay grade. Okay, so it's associative. Okay, so so this is what a curved algebra is. So we're going to have a curved algebra, and now I'd like to define two algebraic objects over a curved algebra.
There's no higher products or anything.
No, it's an
There's
algebra,
no differential either.
and there's no differential. So there's really not much there. That poor little guy. Okay, so what I'd like to define, Zoltan defined it. I want to remind you. We called them type D structures. I regret the day we called them those, but we did.
So do we.
What's that?
So do we.
Oh wow. So if you like, they're free left modules with a choice of basis. So, but free left differential modules with a choice of basis. Or equivalently, you have a vector space X and a map from X to A tensor X.
X is not a vector space.
Why isn't it a vector space? It's a vector space.
Okay.
It's a K module where K is the ground ring. Okay. Okay, so there's a map from X to A tensor X, and it satisfies a structure relation which, if I had had a differential in the algebra, would have looked like this. Except we have curvature, so there's this tree as well. But we have no curvature.
Co-modules.
Yes, X is a co-module. X is a co-module.
The opposite algebra.
Yes, that's right. Notice that, or so equivalently, you can think of X as as this operation is determined by a matrix whose square is a multiple of the identity element, which is the multiple being the curvature. So this is the structure relation. Pardon?
Talking about Jack, the generator of Clifford algebra. Makes you square the opposite identity.
Yeah.
If it was
Okay.
zero, it would be the exterior algebra.
Yeah. It's also like a connection with some specified curvature.
Oh, everything's the same.
Yeah, everything's the same. Okay.
So Venus, the module itself is not curved. It's an uncurved.
It's
module
curved because of this term.
No, but that's the curvature of the algebra.
Well, but you see, the curvature of the algebra, you see.
Oh, because it's free. Yes. Okay. So.
Okay, good. That was a meaningful interaction. Okay, good. So this is what we have from one side, and from the other side we have, of course, I should make 2 points. One is that these are matrix factorizations that Khovanov and Rozansky used to construct knot invariants, and this structure is also prominent in the work of Fukaya Ono Ota. Oh, this is well known in symplectic geometry. So these are structures. This idea of curved A-infinity categories has already well known in symplectic geometry. So let me now, with that said, define something else that's well known in symplectic geometry, and that's the notion of a curved A-infinity module. And so the curved A-infinity module is on almost chain complex. So it's a vector space Y equipped with a differential, except it's not quite a differential because the square of the differential is multiplication by the curvature. And it has an action which is so this is the differential called M1. There's an action M2, which is a map from Y tensor A into Y. which is almost satisfies a Leibniz rule. If I take the algebra element, do a differential afterwards, or I do the differential first and then do the action, and then that should be equal to some other funny term involving the curvature. Where this new creature is also the creature that shows up in the failure of associativity. So if I try to associate, I've got a module element and two algebra elements, then the difference between that and acting by the product is given by the differential of this funny new triple product, where by differential I mean I put the differential before and I put the differential after. This is some homotopy. And of course, well, what else is there? There's all these terms that involve putting the curvature here. Let me try to and keep going. So that is to say, you have an MN action which has got n one incoming module element, n minus one incoming algebra elements, that satisfies an A infinity, these so-called A infinity relations. Okay. Are there questions? It's okay. Misha's gone.
Simon and I both agreed while we were having our naps that you had the same, you wondered as Christopher Zeman with your enthusiasm and your waving of arms, and there's a certain facial likeness too.
I'm glad that someone's getting something out of this talk. Good. Okay.
The first half, I think that I come back to the second half later on.
Okay.
I couldn't resist. You really do remind me of Christopher Zeman.
Okay.
It's a great tribute. He was an extraordinarily stimulating man. Anyway, it's really enthusiasm.
Okay, thank you. All right. Where were we? We erased it. That's right. Okay, so
Excuse me.
yes.
So now in your curved A module, so now again as in curved algebra, there's no differential anymore, or
There is a differential. This is the differential in my curved A module. It's not quite a differential. When you square it, you get multiplication by the curvature.
algebra itself. Can you repeat?
The
The differential of the algebra has been set equal to 0.
Yeah, but the differential of the modules is not 0.
Okay, that's where you add extra terms like.
So if you square the differential of the module, you get multiplication by the curvature, and then there's an action of algebra on the module, which satisfies some relation. Okay. All right. So okay. So what I'd like to explain now is a pairing between type D structures and A infinity modules. So I put my type D structure on the left and my type A structure on the right. And what I want to say is, so I guess I even used letters at some point. Here's X and here's Y. So we put a differential on Y tensor X. And the differential is going to have the following infinite sum of terms. The first is that you just apply the differential on the Y side. The next term is that you apply the delta operation on the X side. Out comes an algebra element, and it acts on the A side. Okay, and the next term is that you apply the differential on the D side twice. Out come two algebra elements. They act at the same moment on the A side, and so on. So you have a string of n times you apply the delta operation. Out come n algebra elements, and they all come in and act on the A side at the same moment. Okay, so the first observation is that delta squared equals 0. So if and that's an exercise in the structure relations. So this is actually a chain complex, and it's an honest chain complex, not a curved one, because your D structure and your A structure were both curved, and somehow the curvature comes out in the wash. So this is some formalism. Now, the same curvature, yeah. So if you're not doing mod 2 coefficients, then you can put in signs everywhere and you still get the same result. Okay, so I should of course say that this algebraic structure was kind of used in 2008 by Lipschitz.
I didn't catch that remark about if you weren't working modulo 2, this d squared equals 0 would still be there or be replaced by something else?
It was not replaced by something else. You have to put in the signs carefully, and then you'll get d squared equals 0. So in 2008, Robert Lipschitz, me, and Dylan Thurston worked out something we called bordered Floer homology, which is an invariant for 3 manifolds with boundary, and it was for reconstructing HF hat, which is one version of Heegard Floer homology for closed manifolds, and the algebraic formalism was almost identical to the one I'm describing right now, with the exception that in that case we sort of very carefully had curvature equal to 0, so we weren't talking about curved algebras. Algebras did have a differential on them, so it was a little bit different. But this formal framework is very reminiscent of bordered Floer homology. Okay, and the techniques are also mostly the same. Okay, so what's the picture now? I've managed to erase it. We had our Heegard diagram for the knot. We cut it into a top and the bottom, and our job now is to associate a type D structure to the top and a type A structure, an A infinity, a curved type D structure to the top, and an A infinity module to the bottom. And the theorem states that the knot Floer homology chain complex is computed by this tensor product of the type D structure with the type A structure. That's the first basic pairing theorem that we're going to need. The computation is sort of an elaboration on that pairing theorem. So I'm going to say what I can, and at some point I'll run out of time and I'll stop. Okay, that's the structure of my talks, in case you were wondering. Okay, so let me now describe what we associate to the top. So let me just sort of try to avoid getting stuck on numerology. So to recall, we cut our Heegard surface in such a way that I'm not going to draw the whole picture, I promise. But so we cut our surface into 2 pieces, one of which has genus G1 and another genus G2. The middle piece has, so this is going to be, I don't know, let's call it sigma 1 and sigma 2. The boundary of sigma 1 is 2n points. There are 2n minus 1 alpha arcs that connects those 2n points. And there will be a bunch of beta circles up here. How many are there going to be? Well, they're going to be G1 plus n minus 1. And there's going to be some alpha arcs. There are 2n minus 1 alpha arcs, and they're going to be G1 alpha circles. And they're going to be, down on the bottom, they're going to be G2 alpha arcs. And they're going to be 2n minus 1 alpha arcs, G2 alpha circles. And it turns out here there's going to be G2 plus n beta circles. So the point is that somehow, like, if you glue together the two surfaces, then there's going to be extra genus of 2n minus 1 coming from gluing these two pieces together. And there's going to be kind of one extra beta arc down here than up here. So for that reason, we call an upper diagram a surface with boundary it's a surface with boundary sigma of genus sigma 1 of genus G1. It has G1 plus n minus 1 beta circles that are pairwise disjoint homologically linearly independent. It has 2n minus 1 alpha arcs that can, it has 2n boundary components. 2n minus 1 alpha arcs that connect the boundary components into a linear chain, as I drew earlier, and it has G plus n minus and G1 alpha circles. Okay, so let me draw a picture. Here's an example. Here's a planar surface, G equals 0. There's a single n equals 2, G equals 0. There's a single beta circle. There are no alpha circles. And there are these 3 alpha arcs. Okay? And what we'd like to do is we would like to, so what I'm trying to define is the D module or the D structure associated to an upper diagram. And rather than giving a definition, I'll do an example. So in this case, we have alpha 1, alpha 2, alpha 3, and beta. The generators of this module, the vector space, is generated by intersection points between this beta circle and this big alpha arc that you get by assembling all those pieces together. So that is to say, there are these 3 generators, A, B, and C. And now what I'd like to do is I would like to put some labels near these boundary circles. So I'm going to write this L1, R1, L2, R2, L3, R3, and L4, R4. Those are labels which actually secretly are going to correspond to algebra elements in an algebra, which is all time defined. But let me just draw this picture here. So there is, if we think of these not as boundary points but as punctures of on this P1, then there's simply a holomorphic disk that goes from B to A and crosses this R2. And what we're going to note that's going to be recorded by saying that the differential of B is equal to R2 times A. Plus, there's also this disk right here that says that the differential of, let's give you another term, which is a, let me actually write them linearly like this. Here's A, B, and C, and I'm drawing the differential. The differential of B is R2 times A, and there's another term in the differential of B, which is L3 times C. And now, there is also a holomorphic disk right here that goes from A back to B. So it's going to pick up this L2 plus, there's another term, L2 times, that comes from the fact that we're actually, this disk completely covers this puncture. So I'm going to call that puncture, that puncture is somehow the product of L4 with R4, which we're going to call U4. This is the U4 that appeared already in Zoltan's talk. And similarly, there's a differential back from C that crosses R3 and U1. So this is our curved complex. Let's observe the fact that d squared does not equal to 0. So there's the differential that goes from B to A, and then there's a differential that goes from A all the way back to B, and there's that one-dimensional moduli space that has one end, which is a broken flow line, and another end, which is a holomorphic disk with boundary in the betas. A boundary degeneration, one of the things that's familiar in breaking Floer homology usually. So the square is so for example, if I do A, come out here, and then I come back, then my square is L2 U4 R2, L2 times U4 times R2. That square, I have some relation which says that L2 times R2 is what we call U2.
Is this saying that right at the beginning of the talk, you said the definition was you took the Floer theory of these Lagrangians? Is
That's
that
right.
saying that's not really
I'm saying that
exactly defined?
globally it's true and it's fine, but when you cut the Hegardt surface into pieces, then it stops being true. And when you cut the diagram into pieces, then you have to look at these, then your Lagrangians stop being normal Lagrangians. They sort of become these things that go out to infinity, and then you start picking up curvature. That's the lesson here. So when I go around here twice, I pick up this U2 times U4. When I go around here twice, I pick up U2 times U4 plus U3 times U1. I go around here, I pick up U3 times U1. So the d squared no longer equals 0. It's a but it's the charge. So that's how we define the D structure. Are there any questions?
Is it the end of the lecture or not yet?
It's not yet. I still have like a full 5 minutes, right?
So your definition of this structure assumes that you only use genus zero thing on planes. In general of this boundary operator, you use this something like higher dimensions or some higher dimensions.
I was being unfair. I was being a very simple case. In real life, there's genus. There's more than n equals 1. We're looking at holomorphic curves in a symmetric product, and I suppressed all that. So I apologize. Any other questions?
Did you tell us what the curved algebra was?
Yeah, I did. Any other questions? No. A curved algebra is an algebra with.
But which one?
Oh no, I didn't. I didn't tell you what the. Sorry, I apologize. Zoltan told you what the algebra is. If you like, the way to read off, I didn't say all the hypotheses on an upper diagram. The other hypothesis on an upper diagram is when you cut it along all the beta circles, then that's going to divide the Riemann your surface into a bunch of components, and each component is supposed to have 2 boundary components in it. So, for example, if I cut this guy, then I've got this boundary component and this guy on one side and that on the other side. So I want exactly 2 boundary components in each component of sigma minus all the beta circles. That's a hypothesis that I want. And with that said, the curvature is the thing that you get by each of these boundary components. I've labeled them, and I just take the corresponding u's and multiply them together. So this curvature is going to be u2 times u4 plus u3 times u1. If you remember, Zoltan defined theseCij's whose differentials were ui times uj. What I'm doing right here is I'm just taking the sum of the uij's. And what I've effectively done is I've somehow, and the algebra that we're working with is the one that Zoltan defined. He called it A, except what I'm now doing is I'm just going to forget about the fact that it had the C in it. And I'm going to think of DC as being the curvature. So one could work in A. It's technically easier to do the holomorphic counting in B with the curvature. Okay, any other questions? Okay, so now let me sketch.
Just point out that you got the curvature u to u4 occasionally and u to u1 occasionally.
Yeah, the other term is 0. So I always, the curvature, in fact, is always u2, u4 plus u3, u1. Zoltan's point is that there's a u3, u1 in here as well, but there were some relations in the algebra which meant that that was 0, and that's why we didn't see them. Sorry, that was Zoltan's point. Okay. Okay, so let me now sketch the construction of the type A module in my remaining 1 minute, and then I'll prove the pairing theorem. So unless there are questions. Any questions? Okay. So again, this is sort of familiar to people who know about bordered Floer homology. The type A module is going to be defined by once again, looking at holomorphic curves. I'm going to just draw an example here. So let's pretend that here's like L1 and here's L2. Maybe this is R1 and R2. I can't remember. So now we're going to look at holomorphic disks. And this holomorphic disk that goes from P to Q, in this case, is going to be interpreted as an action where P has an M something action on it, M3 action, with an incoming R1 algebra element, incoming R2 algebra element in that order, and outgoing a Q. So you go out to the boundary a bunch of times. Each time you go out to the boundary, you pick up an algebra element, and that's the type A module. Okay, so now in my remaining 0 minutes, I'd like to sketch the proof of the pairing theorem. So the way the pairing theorem is proved is that at the first step, you degenerate your Heegard surface. And it turns out that the holomorphic disk counting in the big Heegard surface can be identified with counting points in a fiber product of two moduli spaces. You have a moduli space of holomorphic curves coming on the sigma 1 side, a moduli space of holomorphic curves coming from the sigma 2 side, and there's a fiber product over the disk with a bunch of a symmetric product of the disk. So where you go out to the boundary, on the left-hand side, it's supposed to agree with where you go out to the boundary on the right-hand side. So that is to say, there's some conformally invariant distances between these various mark points. Those should match with the distances between those mark points. So conformal parameters, real numbers, these are not the stuff of algebra. So what we'd like to do is we'd like to modify this description. What's novel in what we're doing now is that we have certain Rabe orbits as well. But let me suppress that. I can explain how we do that to whoever's interested, and tell instead the point of the story that really goes back to the paper with Dylan and Robert. So we have these fiber product, and what we'd like to do is we would like to what we call deforming the diagonal. So instead of counting holomorphic curves, where these conditions are exactly matched, which is what you get from holomorphic geometry, we're going to throw in a parameter t, which rescales on one side with respect to the other. So that is to say, all these conformal distances are multiplied by some factor, and we want that to match with this. So for each number t, you have a chain complex whose differential counts kind of somehow t-matched curves. And then what you do is you let t go to infinity. And when t goes to infinity, what happens in general is that that if I've got holomorphic curves on this A side, they're going to be infinitely separated with holomorphic curves on this side. So these are separated by some finite distance. That gets multiplied up to infinity. So we've got sort of infinitely separated, a sequence of infinitely separated flows on this side. And we've got a marking here. And moreover, what happens if you have more than one marking here, they get squished together on the A side. So we've got lots of marking. We've got several stories on the D side, one story on the A side. Each time you go out to the boundary on the A side, you get a different story on the D side. So this is you might think, a horrible holomorphic object. But in fact, it's exactly one of the terms that I described in this tensor product. So when this t parameter goes to infinity, somehow all the analysis turns into algebra. And I should make one last statement, which is how this is different from what we had earlier. What's different now is that there are holomorphic disks. There's these boundary bubbling that can happen on the D side. And that's what gives rise to the curvature. And I apologize, I haven't explained that better, but whoever's interested can hear about that in more detail later.
Yeah. All right, Simon, you come first.
This is a two-part question about the relation with Cyber-Britten equations. For example, this the bordered Floer theory you mentioned. Is it, does that have a Cyber-Britten version or interpretation?
That's an excellent question. It's possible that I'm not the person to answer it.
But the second part was whether the particular constructions you're doing, I mean, it sounds that some of it could be translated into the stretching the neck, could be, but maybe the last thing is more subtle that you wouldn't see.
Maybe. Let me say something which I like to say to everybody who's willing to listen to it, this is possibly due to you. This is possibly due to you. So if you have a surface, then you can look at three manifolds with boundary identified with that surface, and you can associate the Floer homology, whatever version of Floer homology you like, to. So we're going to define a category whose boundary is whose objects are three manifolds with boundary bordered identified with F, and and the morphism spaces between two three manifolds like that is going to be the whatever Floer homology chain complex you'd like to associate to -1 U1 union U2, and if you have three of these, then you construct this four manifold and put infinite ends on it, and the map from U1, so minus U1 tends to U2 CF minus U2 union U2. You look at the four manifold invariant here. This should be the CF of minus U1 union U3, and then you would have higher products when you have to have four of those. Then not only do you have a four manifold with three incoming and one outgoing boundaries, but you have a one-parameter family of necks that you can do. So that would define for you a higher product, and so on. And one could imagine that this A infinity category is isomorphic to that A infinity category. That's what one would imagine.
Maybe I can ask my question now. Don't quite know where to start. Obviously, listening to your lecture, I try to understand it in my own terms. I may fail to understand, but looking at what you've got up there, I'm struck by the resemblance to what people did in the days when, well, they tried to understand spectral sequences, but they didn't understand them very difficultly. And what I think I see there is a spectral sequence not being used. I see exactly all the ingredients of a spectral sequence. I know what a spectral sequence is. It goes back to Costolere, but been reinvented by many other names. And that spectral sequence, well, from my point of view, to involve index theory and K-theory, that's natural. And so I see that you get a topological invariant you understand to calculate, there's some difference in dimensions, being configured as an index, and your spectral sequence helps you to do that. And the whole beauty of the spectral sequence is we didn't need to think, you just turned a handle, and the answer came out. If you wanted to analyze what had up in the spectral sequence, unbolt it, throw away all that beautiful machinery, you would look into the inside workings of the spectral sequence, and you would draw exactly that diagram. That diagram is what's drawn by somebody who's never worked with the spectral sequence before.
Okay.
And now, maybe you're wrong. Maybe you know all about spectral sequences, but from my point of view, that is what people did.
But you're not supposed to work with spectral sequences. You're supposed to work with chain complexes, not with spectral sequences.
But where does spectral sequence come from? Double chain?
You had chain complex. That's better than a spectral sequence.
No, it's not. Christopher Zeeman, his thesis was about what's called dihomology. He had double chain complex, chain and cluster, and that led him to spectral sequences, although he didn't know.
Okay, so let me. Okay, so.
Sorry.
No. That's absolutely fine. But in fact, it's perfect. So let me say a spectral sequence. So the spectral sequence I would say here is kind of silly. It would say something like it's a two-step spectral sequence. But no, we can make it interesting. Let's make it interesting. So if you have a knot with a bunch of crossings, then I didn't tell this story, but to each of those little crossings, you would associate a bimodule. And we could do a spectral sequence whose E2 term is the homologies of those various bimodules. Its higher differentials are something, and it eventually converges to knot-Floer homology. But what we have is better. We have bimodules whose actual, and a model for a tensor product, which when you tensor them together actually gives you the chain complex you wanted. So if you want to, you could take homologies locally and then get a spectral sequence. And in fact, in this spirit, using bordered Floer so in this spirit, Zoltan and I, back in 2003, constructed a spectral sequence from the Khovanov homology of a knot to the Heegard Floer homology of the branch double cover of the knot.
I would do it differently. I would just construct the spectral sequence associated to equivariant K theory in the fibers, and I would get exactly the same story.
Okay, well that I can't
think
do.
It would be easier for me because I know all the ingredients.
Okay.
For you, you'd have to unwind it in your language, and this is your translation. That's fair enough.
Okay. Okay, then I don't know.
If you do that spectral sequence for this example, then you just get the chain complex on Kaufman state. Where the E1 pages you probably the Kaufman state.
No. You see, it depends on how you do the tensor products, right? You would.
I feel like I've lost control.
Okay, I'm sorry. That's an interesting question. Well, we should, but yeah.
Okay, Ozsvath, stop.
Yes, sir.
Thank you very much.